Good day. Welcome to the 15th lecture of metal forming. So in the last class, we discussed the open die forging, analysis of open die forging. We determined the forging load or the pressure distribution under three cases. And next, in this lecture, I'm going to explain the other two types of forging, that is impression die forging and closed die forging. Then I will explain different miscellaneous forging operations. So here in the open die forging, as you know, we forge in between two flat dies. So the analysis of the open die forging is somewhat simple than that of the impression die forging and closed die forging, because in impression die forging actually there is a cavity inside the die, and the material is actually deformed inside this cavity region. So the analysis of this impression die forging is somewhat difficult compared to this open die forging. So here in this we can see the impression die forging. We have a cavity here. This is the area where we place the workpiece and we apply the compressive force by the movement of upper die and bottom die. And when the die moving uh, and applying the compressive force, the workpiece, the yellow color workpiece is deformed exactly with the similar shape of the cavity. And after a particular amount of deformation, a flash is formed in the parting line region. We can see the flash formation, and we can see this is the output workpiece, and along this region we can see the flash. Okay, the flash is formed, and in the last lectures I already explained the importance of flash formation. So here in the flash region, I already explained that this A by S ratio is very high in the flash region. This is A and this is S, the small height H. So A by S ratio is very high in the flash region. The pressure is proportional to A by S ratio. So for any material flow or metal flow in the flash region require huge amount of pressure compared to the area in the bulk region or in the cavity region. So this flash formation allow the material to completely fill the entire region of the cavity before moving through the flash region. So this flash ensure the complete fill of the cavity in case of impression die forging. And when we look on the different terminologies in the impression die forging, we can see this is the gutter region. I already explained that this is this flat region, horizontal region of the flash is called land, and this region is called gutter region. This is the parting line which is separating the upper die and the bottom die, and this is the web of the final workpiece, and this is the rib of the final workpiece. And we can see a fillet here. Instead of sharp corners, here is a fillet, and this is the sharp corner. This is a sharp corner, and the flash is formed here. This is the flash which is formed, which has a two area, land and gutter region, and that is the different terminologies associated with the impression die forging process. Then I already explained here in case of open die forging, the analysis is somewhat simple because we know what is the deformation, how much amount of stress in particular direction. So we can consider the equilibrium in the horizontal direction. So the analysis is somewhat simple. But in case of closed die forging, the analysis is very difficult. What is the reason for that? So in case of closed die forging, here the coefficient of friction will be a particular value, but here the coefficient of friction will be another value, and the actually the deformation inside this cavity is different. So the flow stress will be different in different regions, and the amount of stress developed during the deformation also will be different. So this is actually a complex state of condition. So conventional analysis is not suitable for impression die forging. We need to use FEM analysis, etc. for impression die forging. But for the simplicity, we can use this equation. We can use this equation for impression die forging. So this is in this case We know we already derived this equation in case of a open die forging without friction, that is flow stress into area. That is the amount of force required for the deformation if there is no friction. So here we multiply this equation with a value called Kp, a multiplying factor Kp. So actually this multiplying factor is used here to simplify this analysis, or to simplify to develop this forging force with a simplified analysis. Here we have a value for this Kp. 3 to 5 range value is given for a simple shape. If the impression die forging is for a simple shape without flash, we give the value between 3 and 5 for Kp, 5 to 8 with the flash, and 8 to 12 for complex shapes impression die forging. So we can supply the Kp value either 8 to 12 here, or 5 to 8, or 3 to 5. Then we can calculate the forging load. So F is the forging force, and here the area. Area is nothing but it is a projected area, because this is a very complex cross section. In case of impression die forging, we cannot say a particular cross section for the impression die forged component. So we use a projected area to calculate the force, and sigma F is nothing but that is the flow stress of the material. If the material is a perfectly plastic material, then sigma F is equal to sigma Y. And if it is a strain hardened material, then sigma F is the flow stress of the material. And it's dependent upon the material type, strain, material strain rate, temperature, etc. So we use this formula in case of impression die forging. F is equal to Kp into sigma F into A. That is a very simple formula in case of impression die forging. And when we check the amount of forging load during the forging operation, impression die forging operation, we can see when the force cavity is filled gradually, the force is increasing gradually. See this, this is the first stage. In the first stage, the actually the two dies, upper and bottom dies, are come close to each other, and it starts to touch the workpiece. So some amount of deformation has happened there. So we can see when the die touches the workpiece, the amount of force is increasing. This is the curve showing the increase of force. Okay, when the die touches the workpiece. Then again, when the die move close to each other, the deformation is continued. So we can see there is a deformation here, deformation of the workpiece. So during this deformation, we can see the increase of force required. Okay, along the deformation, uh, when the deformation is continuing, we need to apply higher amount of force. But this is a gradual increase in force. In this region, this is a gradual increase in force. But at a particular stage, when flash is formed, flash is formed. That means when the flash is formed, the uh, cavity almost filled with the material. Not 100%, but the cavity is almost filled with the material. Then after the formation of flash, we can see a sudden rise in force. Sudden force rise in forging force. What is the reason? When the flash is formed, the material has to flow in a very sharp corner. The remaining area or cavity area to be filled is very sharp corners. So the material has to flow into the very sharp corners. For that, we need to apply very higher amount of load. That is why after the flash area, the load is increasing in a steady manner. Okay, we can see the steeper increase of the forging load. But up to the flash formation, the increase is gradual. Okay, so this is the starting point of contact of die and workpiece. This is the completion of forging. So at the end of the completion of the forging, we require maximum amount of force when the die is completely closed. That means this stage required maximum amount of force, but the initial stage required minimum amount of force. Okay, so this is the variation or distribution of the force when this die approaches and when impression die forging, during the impression die forging. Next one is closed die forging. So there is a actually almost similar. The impression die forging and the closed die forging is almost similar. The main difference is that in case of impression die forging, the flash is formed in between, in the gutter area and land area. Flash is formed in case of impression die forging. That means there will be some amount of extra material we will supply with the workpiece for the formation of flash. At the end of the process, we machine the flash. This is the flash area of the workpiece. We machine the flash region. That is a scrap material. So we provide extra material during the impression die forging. Actually, the extra material is flowing through the flash area. But in case of closed die forging, there is no such flash formation. Okay, that actually the closed die forging is the workpiece is completely surrounded with the die. There is no such flash formation. Or we can say we actually supply the workpiece with the exact similar volume of the finished product. We not provide extra material for the flash formation. Okay, so there is no flash formation. So in this case, we need to control this process very properly. So for volume of the material is essential to a forging, obtain a forging of desired dimension. So proper control is required. If proper control is not there, what happened? The forging with the incomplete filling may be developed. The entire material may not flow into the sharp corner regions. If there is a flash, actually after the flash formation, high pressure will be developed. Under this high pressure, the material can flow in the very sharp corner regions. We got a sound cast product, forged product. But here in this closed die forging, there is no such flash formation. So we need a proper control of the forging process. Then undersized blank will prevent the complete filling. So if the blank size is undersized in the workpiece, then it will prevent the complete filling. And if we give oversized blank, the workpiece is oversized. Extra material is provided in the workpiece. What happened? The extra material may cause the failure for the uh, die or the final product, or there is a chance for the jamming also, because the extra material will not go outside. There is no flash area, so extra material does not have any space to occupy inside the cavity. So this extra material may cause the failure of the die or jamming of the forging operation. So this is called a closed die forging. So we studied three: impression die forging, closed die forging, and initially we studied the open die forging. Next, we will study different miscellaneous forging operation. The important three miscellaneous forging operations are coining, they are skew rolling, and roll forging. And in this roll forging, we already discussed in the rolling area when rolling lectures. What is coining? From the name itself, this is used for making of coins, basically. So we know for the making of coins, we use the method minting of coins. So this is a closed die forging method. But what is compared to other forging, closed die forging method, what is the importance of coining? In case of coin, when we make a coin, very sharp projections and impressions are uh, we can see in these coins. We can see in this coin. See this very sharp. Okay, so this sharp impressions or projections is very difficult to make by forging. So in coining operation, we supply a flow stress, the extra supply the pressure or the vertical force, which is 5 or 6 times higher than that of the flow stress of the material. So what is the reason for the very high amount of pressure application? When we apply very high amount of pressure, we can reproduce the very narrow or projections in the coils, very narrow projections. Okay, so by this application of high pressure, very little change in the shape can be produced by this forging method. So that is why we apply very huge amount of pressure in the coining process. And actually for the coining, this is not a single process. It's a several operations do in a continuous manner for making a blank into a coin. Here we are not using lubricants. When we use a lubricant, what happens? The lubricant occupy in this region. In this region, the lubricant is occupied this region, and this will prevent the exact impressions and projections on the coin. So we are not using lubricants. So coining operation is to force the impressions on the die. So actually, in die we have some impression. So that is actually forced against the blank and produce projections and impression on the workpiece. So this is a closed die forging operation. So we can see different coins produced using forging operation. Next one, we already discussed the roll forging operation. This is actually a hybrid of rolling process and forging process. Here we have two rollers. See this, two rollers with the grooves. We can see grooves here. See this grooves we can see in the some portion of the roller. So when these two rollers rotating and we fit the workpiece in between the gap between the two rollers, what happened? The grooves provided on the roller deform the workpiece, and we got very complex products we can make using this rod forging operation. Next we will see a video of rod forging operation. Actually it is not a very clear video, but we can see the roller here. So this is the workpiece, and here we can see the roller with the grooves. Okay, we can see two rollers. This one is first roller, this is the second roller, and this area is flat. This is actually a cylindrical area, but this area we can see with the grooves. Actually this, when the roller rotating, this grooved area producing impression on the workpiece. See this. After the rod forging operation, the shape and size of the workpiece is changed. Okay, so similarly this type of grooved rollers are rotating, and we can produce complex crankshaft, connecting rod, other automotive components can be made using this rod forging methods. And third method is called skew rolling. This is commonly used for making ball bearings. Ball bearings. So here also we use two rollers with the these grooves on the roller. So the round wire is, this is the round wire which is fed into the roll gap, and spherical blanks are formed continuously by rotating rods. And here we can see this is the spherical balls is produced from the rod by skew rolling process. This is the grooved rollers, and we can see a video how this rod converted to spherical rod balls. So here it is rotating, and we can see this ball, spherical balls is developed from the rod when it is passing through the gap between these two grooved rods. Okay, so this is called skew rolling operation. So this is the first method for the production of ball bearings. Second method, we can use this setup. So we kept a blank here, and we support with the two ejectors and the die, and we support the blank. Then we apply force against this blank, and we change into spherical shape. So that is the second method for the production of ball bearings. Okay, and after the production, we can forging, we can do polishing and other works to make the good surface finish. So that is the skew rolling process. Next we will discuss different defects associated with the forging process. We already discussed different defects in the rolling process. So similarly, here there are different types of surface related defects are there. So when we do forging operations after barreling, so this is the top view of the barreled product. There will be some cracks develop on the surface of the barreled product. This type of cracks will be developed. And what is the reason? During the barreling, some amount of tensile stress will be developed on the material, and this tensile stress is creating such type of cracks on the surface. So that is the first defects we can see in a forged component. Second defect is a lap defect, and in this lap defect the web portion, we already discussed the what is the web of the final product. This is the web portion. If the web portion is very thin compared to other regions, what happened? During the forging process, the web portion fold itself like this. Okay, instead of converting the web like this, actually the final product will be like this. This is the final procession of the final product. Okay, but here we can see the web is very thin. So during the forging process, when we apply the compressive force to the die, the web starts to fold itself. See this folding of the web. Then after the completion of the forging operation, we can see such type of lap defects. This is because of the self-folding of the web area. That is the second defect, lap formation. And how can we avoid this lap formation? Web thickness should be increased. The web thickness is increased, then this type of bending of the web can be avoided. Thereby, this lap formation also can be avoided. So that is the next defect. The third one is the internal cracks. So during the deformation of this type of workpiece, we can see in this stage, in the second stage, the forging is started in the first stage. The second stage, almost entire material is filled in the die cavity. Entire material is filled in the die cavity, but we can see a gap between the two die here in the second stage, but the entire material is filled in the die cavity. So again, when the two die approach each other, what happened? The material in this region starts to flow in the outward direction. The material in the center region, already the material in this die area, this area already filled in the die cavity. So when again, but these two dies not completely approach to parting line. So then further in the third stage, what happened? The material in the center region starts to flow through this already filled regions. Material in the center region flow outward. This outward flow from this web region through this already filled cavity region create some internal cracks. Okay, so if the web thickness is very large, the excess material from the web region material flow past already forged portion. This is already forged portion. Okay, so the center region material in the web area starts to flow through the already forged region, and this flow of metal flow leads to a crack that is called internal crack. So how can we avoid this? Reduce the web thickness. So we need, if the web thickness is very small, lap defect is formed. If the web thickness is higher or thicker web is used, then internal crack will be formed. So there is a optimum web thickness to avoid these two defects. And third one is the cold shed. Cold shed. So the cold shed is mainly because of the shape of the die. Here we can see, in this case, these are the 6 stages of forging operation. In the first stage, we apply the compressive force. The material starts to flow through into the cavity. So the material is not completely filled here. Some amount of material has to enter to the cavity region. Here almost the material is filled, but here we can see in this region, Here we can see this is a sharp corner region. Okay, this is a sharp corner region. So here in this region, the material will be filled like this. There will be some cavity region in the sharp corner regions. Okay, during this forging process, the material in this region is actually fold over itself like this. Here we can see the material fold over itself, and it make a cavity here, a void space here by this self-folding of the material, and this is called cold shuts. And the main reason for this cold shut formation is this sharp corner in the cavity. To avoid cold shut, instead of using a sharp corner, make a fillet here. Make a fillet corner here. So the material can flow easily through the fillet region, and it can completely fill without any voids. So that defect is called a cold shut defects. And this cold shut may leads to the factory failure and a corrosion wear, etc. So we can see the cold shut here, the self-folding of the material during the compression. This is because of the sharp corners in the cavity. The last defect, the grain flow. So during the forging, we already discussed the grain flow pattern. After forging, if it is an upsetting process, the grain flow pattern will be like this. This is the grain flow pattern. Okay. Okay. So this type of grain flow pattern, here we can see some grains actually perpendicular to the surface. Okay. So the grain flow lines may reach the surface in a perpendicular direction, and this grain boundary exposed to the environment. Actually, we know in the grain boundary regions, the atoms are not perfectly bonded. Okay, so these atoms which is in the free state, some atoms may be in the free state with a higher energy level. So these atoms may react with the different gases and other water, acids, etc. in the atmosphere, and may cause defects in the surface. Okay, so this type of grain flow pattern may affect the surface by the reaction with this grain boundary constraints with the atmospheric constraints. So, and that also act as a stress riser. So we should select a grain flow pattern. When we forge a component, we should design the grain flow such that should not be there any grain at end of grain perpendicular to the surface. And as we know, after the forging, we got only anisotropic material. In different direction, the strength or other properties will be different. That is also we can consider as a defect. And these are the different defects associated with the grain flow pattern. Then pitting, the small depression on the surface of the forged parts. Uh, we already seen one component after forging in a video. Some pitting. It's not a perfectly finished surface. Some pitting on the surface. Some scales and oxides. Maybe in the upsetting when I discuss upsetting process, we have seen a scales is removed from the workpiece. So such type of scales when trapped on the die interface region may cause this type of pitting related failure. Mismatching. So for example, in the cold die forging, if this top die and bottom die is not perfectly aligned, the final product will be a mismatched product. Okay, so that is also a defect. Blowholes, similar to this casting process, we already discussed these blowholes. In forging operation, the already in the ingots after the casting, there may be some blowholes. That blowholes also may be there after forging operation. Then some dirt, sand, slag, etc., which is already present in the ingot workpiece, may be also a forging defect. These are the different types of forging defects. And when we consider the economy of the forging process with the other manufacturing process, we can make a connecting rod with a different process. We can use sand casting, permanent mold casting can be used, forging can be used, investment casting can be used, die casting can be used. So there are different processes for making a connecting rod. And how this connecting rod can be made economically. So the production cost of connecting rod manufacturing is related to the number of pieces made. Okay, the cost per piece is based on the number of pieces made. If the number of pieces is less than 100 or around 100, then we can go with the sand casting, because sand casting there is no need of heavy machineries. We need only flask and sand, etc. We can easily manufacture 100 connection rods with the sand casting. So we can reduce the cost of per piece using sand casting. But if you want to make this 1 lakh product, 1 lakh product connecting rod, in that case, the sand casting is not a feasible one, because making of 1 lakh product with the sand casting, breaking of the mold, preparing mold, and breaking of mold is very difficult. So if 1 lakh product is going to manufacture, then we can go with the investment casting. We already discussed that. And the forging, sorry, it's not investment casting. We can go with the forging. See this low cost of forging, very low cost of forging. Okay, so if for a particular company or industry has to, they are going to manufacture 1 lakh connecting rod, then they can purchase a forging machine. Okay, so we already seen in a video the time requirement, production rate of the connecting rod with the forging process. Within second or within minutes, we can make a connecting rod. Okay, so that is the important. If number of components is very huge, then we can use forging operation for the manufacturing. If the number of components is less, then we can go with the sand casting or permanent casting, etc. Mold casting. So that is about the economy of choosing a manufacturing process. So we choose any metal forming process, forging, rolling, extrusion, drawing, etc. when this type of number of components are very huge. Because for any metal forming process, the machine cost is very huge. So the for the trade-off of the machine cost and the cost of per piece, we need huge amount of product or to be manufactured, then only it will be a feasible one. Okay, so that is the about the economy. So up to this I finish the forging process. We discussed analysis, different forging operations, uh, and defects, etc. So from this lecture, I concluding the forging operation. The next lecture, we will discuss the next metal forming operation, that is extrusion process. Thank you.